This video is going to discuss how we can represent negative numbers in digital logic circuits. It begins by looking at a simple representation and pointing out why it is not ideal. It then looks at the 2's complement form of representing negative numbers, which works very well. It is important that we have a system of numeration for digital circuits where we can represent negative numbers to allow us to build devices like calculators or to understand how parts of a modern computer's CPU, such as the accumulator, work. More than just represent negative numbers, we also need to know how we can apply operations such as additions, subtractions, multiplication and divisions to operands that might be negative. So very briefly, we've covered before the way that we can represent decimal numbers in binary. If we want to represent the decimal number 5 in binary, it will be represented as 1 times 4 plus 0 times 2 plus 1 times 1. Or 101 subscript 2 to indicate that it's binary. So 101 binary. Or in general terms, we would have 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 1 times 2 to the power of 0, remembering that 2 to the power of 1 is 2 and 2 to the power of 0 is 1. Anything to the power of 0 is 1. Where we have 2 to the power of the position in the place-weighted system. So this works out to be 4 plus 0 plus 1, which is our decimal 5. So we know how to represent positive numbers. If we have 4 bits, we can represent 2 to the power of 4 different numbers. So it's 16 different numbers in the range 0, 0, 0, 0 to 1, 1, 1, 1, where 4 zeros is decimal 0 and 4 ones is decimal 15. So 16 different integer numbers. So how do we represent negative numbers? Well, the first thing to remember is that computers only understand ones and zeros, which can also be described as true and false. That's it and nothing more. So what you're looking at in this video is millions of ones and zeros, or bits, being used to describe and capture color information and transmit it over a network. That's why your internet connection will be described as, for example, a 10 megabit per second connection, which is 10 million ones or zeros per second. So how do we represent negative numbers? Well, since there are only ones and zeros, there's no negative sign or indeed a decimal point, which we call a binary point in binary. So what's the option? Well, the first way would be to use a 0 to represent a positive number and a 1 to represent a negative number, or the other way around. It really doesn't matter as long as we remember. So if we choose to use a 0 for a positive number, we could write 1101 to represent minus 5, where the first one says that the number is negative, and the remaining bits state that the value of the number is 5, or the magnitude of the number is 5. So that would be minus 5. So how do we represent plus 5? Well, it's written as 0101. So the sign is positive and the magnitude is 5. But we have to be very careful not to shorten the number to 101, as this would look like minus 1 under our number scheme. So the first thing to note is that we need to state and remember what size our number system is. So let's say we wanted to build an electronic circuit that had 5 bits. We could use 1 bit as the sign bit and 4 bits to represent the size or magnitude of the number. So let's develop that system where we use 5 bits, 1 sign bit and 4 magnitude bits. Here's what it looks like, where the first bit is the sign and the remaining bits are the magnitude. So we could say 0 for the sign, 0001 to represent plus 1 in decimal, and 10001 to represent minus 1 in decimal. Now that's not bad. The biggest positive number we can have is 01111, which is plus 15 in decimal, and the biggest negative number, or the most negative number we can represent is 11111, which is minus 15. We know that from before that with 5 bits we should be able to represent 2 to the power of 5 states. So 2 to the power of 5 is 32, so 32 states. So where are the remaining 2 values? Well, this is one of the problems with this system. 00000 represents decimal 0, but so does 1 with 4 zeros. So that's a positive 0 and a negative 0. This will lead to confusion, and it's going to reduce our total number of states from 32 down to 31, so it's wasteful. There's a second problem, and this is probably even more serious. The system allows us to represent a number, so it is a system of numeration. But it is a system of numeration that does not work correctly for basic arithmetic operations such as addition, subtraction. Well, it doesn't always work. So here's an example if we wanted to add two positive numbers together. So for example, if we wanted to add 0, 0, 0, 1, 0, which is decimal 2, and 0, 0, 0, 0, 1, which is decimal 1, we get 0, 0, 0, 1, 1, which is decimal 3. So that's fine and it works perfectly. But what if we add a positive to a negative number? So if we take our 2 again, 0, 0, 0, 1, 0, which is decimal 2, and minus 1, which will be minus, the sign bit will be a 1, so it's minus 0, 0, 0, 1, which is minus 1, we get 1, 0, 0, 1, 1, which is minus 3. So that says that 2 minus 1 is equal to minus 3. Now we know from our decimal system that's clearly wrong. So the system of numeration does not work for basic arithmetic operations. No matter how you try to fix this system, it will not work, and that's why we need the 2's complement form. The 2's complement is a way of representing signed binary numbers or a system of numeration that actually works for arithmetic operations such as additions and subtractions. This fact allows us to build computers that can work with negative numbers. It's a very important system of numeration because even today, this is the way that signed integers are represented in computer architectures. The first step may initially seem counterintuitive, but bear with it. Let's look at the number 0, 0, 0, 0, 1, which was 1 before. We had a 0 for the sign bit and 0, 0, 0, 1 for the magnitude. However, instead of treating the leading 0 as representing the positive sign, let us treat it as representing 0 times a negative place weighted value, in this case minus 16 in decimal. So the number is actually 0 times minus 16 plus 0 times 8 plus 0 times 4 plus 0 times 2 plus 1 times 1, which is integer value 1 or decimal value of 1. The weights of each of the positions are 2 to the n, where n is the position, but the leftmost number is negative. In this case, minus 1 would be represented as 1 times minus 16 plus something, where the something adds up to 15 in order to get minus 1. So that would be 1 times minus 16 plus 1 times 8 plus 1 times 4 plus 1 times 2 plus 1 times 1. So minus 16 plus 15 is equal to minus 1. So 0, 0, 0, 0, 1 represents plus 1, and 1 with 4 ones after it represents minus 1. If this is your first time to see this, you are probably worried that this is much too complex a representation to do something simple like represent negative numbers. But please bear with it, as there are some really good advantages of this system. The good news is that there is a much easier way to calculate the representation of minus 1, and it is to very simply invert all of the bits and add 1. So 0, 0, 0, 0, 1 represents plus 1. If we wanted to get the negative equivalent to that, we would invert all the bits, which would be 1, 1, 1, 1, 0, plus 1 gives 1 and then 4 ones, just as I showed you before. Let's try another example with some other numbers. If we wanted to get minus 2, well, it's the 2's complement form of plus 2. So 0, 0, 0, 1, 0, inverted is 1, 1, 1, 0, 1, plus 1, which gives us 1, 1, 1, 1, 0. So let's try one more example that helps illustrate why the 2's complement is so important. Let's try the 2's complement of 0. So positive 0, if there is such a thing, is 0 and 4 zeros. Positive 0. Invert it, so we want to get the 2's complement of this. Invert it gives 1 and 4 ones. And then add 1. Well, it'll give us 0, 0, 0, 0, 4 zeros for the magnitude, 0 for the sign bit, and 1 additional bit that we ignore. We ignore the 6th one, and so we get 0. So Importantly, there is only one single value of 0, not two like we had in our simple system before. The issue of the sixth value is an important one, and I'll discuss this in the next video. However, for the moment, you can just take it that if you build a 5-bit computer, that it only has 5 bits to represent numbers. It can't have a 6th bit, otherwise it will be a 6-bit computer. The same is true for larger computer systems like 32-bit computers or 64-bit computers. So here is a table for our 5-bit computer of all of the numbers it can represent. So all of the negative numbers have a leading 1, and this is how you know if it is a positive or negative number. But just remember that if you see a leading 1, that the number is in its 2's complement form. Note that this table goes from minus 16 to plus 15. So there are 32 individual values in the range of minus 2 to the power of n minus 1 to plus 2 to the power of n minus 1 minus 1. So we only have a single value of 0, and the number system goes one larger on the negative side than it does on the positive side. And this is because that the 0 value is assumed to have a positive sign, using up one of our positive number states. This would be true for a 16-bit computer. For example, representing signed integer values, it will be able to represent minus 2 to the power of 16 minus 1, so minus 2 to the 15, to plus 2 to the power of 16 minus 1 minus 1, so 2 to the power of 15 minus 1, which is minus 32,768 to plus 32,767. On a 32-bit computer, this is about minus 2 billion to plus 2 billion, and on a 64-bit computer, well, the numbers are represented here. But exactly the same rules apply. So that is the first important advantage of 2's complement. We get the full range of data that we should get and only have one value of 0, which will avoid confusion. The second advantage is we now have a system of numeration that actually works for irregular arithmetic with negative numbers. So let's look at the examples from before. 2 plus 1 and 2 minus 1. So 2 plus 1 will be represented in a 5-bit system where we've one sign bit and 4 magnitude bits as 0, 0, 0, 1, 0, added to 0, 0, 0, 0, 1, which when we do the addition gives us 0, 0, 0, 1, 1, which is decimal 3 as we would expect. However, to do 2 minus 1, we're actually going to do 2 plus minus 1, where we convert minus 1 into its 2's complement form. So the 2's complement of minus 1 is 0, 0, 0, 0, 1, which is plus 1. Invert the bits, it becomes 1, 1, 1, 1, 0, plus 1 equals 1 with 4 ones. So our addition of 2 plus minus 1 is 0, 0, 0, 1, 0, plus 1 with 4 ones. When we add this together, we get 0, 0, 0, 1 for the magnitude, 0 for the sign bit, and we also get a 6th bit, and we ignore this as before. So when we ignore the 6th one, we get 0, 0, 0, 0, 1, which is positive 1, and so the system works correctly. Remember that this didn't work for our simple system, where we didn't use the 2's complement form to represent negative numbers. So it works. But let's look at a slightly more complicated example. Let's look at 1 minus 2, which will be 1 plus minus 2. So we need to take the 2's complement of minus 2, which is 0, 0, 0, 1, 0, inverted to 1, 1, 1, 0, 1, plus 1, which is 1, 1, 1, 1, 0. So we take this and we add it to 1. So 0, 0, 0, 0, 1 plus 1, 1, 1, 1, 0 is equal to 1 and 4 ones. Now, because the leading sign or bit is 1, we know that this number is in its 2's complement form. So it's minus something. It's not minus 15. It might look like minus 15, but we need to find out what the something is, what the magnitude is. So we need to get the 2's complement of the number. So the 2's complement of 1 with 4 ones is, invert the bits, 0 with 4 zeros, plus 1, which is 0, 0, 0, 0, 1, which is 1 in the decimal system. So minus some magnitude, where the magnitude is 1, means that our result is -1. So it works. One very important aspect of this system is that you have to be absolutely rigorous in keeping the size of the system. If we were to use a 4-bit system where we had 1 bit for our sign and 3 bits for the magnitude, the 2's complement values are different. So let's compare. What is decimal minus 5 on a 5-bit system? Well, it's 0, 0, 1, 0, 1, inverted 2, 1, 1, 0, 1, 0, plus 1, which gives us 1, 1, 0, 1, 1. Whereas decimal minus 5 on a 4-bit system is 0, 1, 0, 1, so there's 1 less 0, leading 0, inverted 2, 1, 0, 1, 0, plus 1, which gives us 1, 0, 1, 1. So while plus 5 will be the same, 0, 0, 1, 0, 1, and 0, 1, 0, 1, if you ignore the leading zeros, you should not leave them out, as it'll cause serious confusion when representing the negative values. You will notice that I've treated addition and subtraction as the same operation. If we want to subtract 3 from 5, I simply add -3 to 5. There is a good reason for this, because if we have to build a digital logic circuit that involves a lot of gates to do addition in our circuits, it's possible that by performing our subtractions using addition means that we could build a much smaller circuit at a much lower cost. Before I look at multiplication, here's a few examples for you to try. Perform the subtraction of 15 minus 7 using 5-bit 2's complement form. Perform 15 minus 7 using 8-bit 2's complement form. And perform 22 minus 28 using 6-bit 2's complement form. In all cases, you should use a single sign bit and the remainder of the bits for the magnitude. Obviously, you know what the correct answer should be in decimal, but that's not the point. We need to be able to build logic circuits that can determine what the answer should be for us. So please pause the video now and have a go at doing the calculations yourself, and then I'll provide the solutions. So the first question says perform 15 minus 7 using 5-bit 2's complement form. 5-bit 2's complement means we've 1 bit for the sign bit and we have 4 bits for the magnitude. So this is the magnitude and this is the sign bit. So that's the way that we structure this. So it means that what we want to do now is write out what we're trying to do. So 15, and we're going to use addition for this. It's 15 plus minus 7. That's what we want to evaluate. So 15 in binary, where the sign is positive, so in this case we've positive 15, we use a 0 to represent positive 15, and then we say, well, 15 is 1, 1, 1, 1. It's 4 ones. 8 plus 4 plus 2 plus 1 is 15. Now we want to say add to this minus 7. So we want to add on minus 7 to get our expression. So what is minus 7? Well, minus 7, we've got to get the 2's complement of plus 7. So plus 7 we would write as 0, 1, 1, 1. 1 plus 2 plus 4 is 7. So to get the 2's complement, we first get the 1's complement, which we get by inverting all the bits. 1, 0, 0, 0. So that's the 1's complement. But the 2's complement, we add on 1. So to get this, we add on 1. So 1 plus 0 is 1. Nothing plus 0 is 0. Nothing plus 0 is 0. Nothing plus 1 is 1. So the 2's complement of 7 is 1, 0, 0, 1. So we add on this, so it's minus, so the sign bit is 1. And then our magnitude is 1, 0, 0, 1. So we simply go through now and we add all the bits together. So 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 plus 1 is 1 with a carry of 1. And 1 plus 1 plus 0 is 0 with a carry of 1. Now, as before, this is a 5-bit system. So in this case here, this is the 6th bit. So we simply ignore it because our computer is a 5-bit computer, if you like. So therefore it doesn't have a 6th bit. Which means that the result here is positive because the sign bit is 0. So it's positive. And the magnitude is 8 plus 0 4's, plus 0 2's, plus 0 1's, so the magnitude is positive 8. And that conforms with what we would expect. We would expect that 15 minus 7 in decimal would give us a value of 8. We know that. But that's not the point. The point is now we're starting to work towards a system where we can build circuits that are able to do this type of arithmetic for us. So the next question is almost the same as before, with the exception in this case it says you perform 15 minus 7 using 8-bit 2's complement form. Now 8-bit 2's complement form is different than the previous question because we have 8 bits to represent our number. So 1 bit for our sign bit and 7 bits for our magnitude. So now if we write 15, so 15 is what we're going to be using, and we're going to be adding on minus 7. So 15 in this case is 0, and we have 7 bits now to represent our magnitude. So if you remember, it was 4 ones in a row, so it means we've got 7 bits. So that's 15 in 8-bit 2's complement. So we can see we've used 8 bits in total, 1 for the sign bit, 7 bits for the magnitude, 1 2 1 1 1 1 2 1 4 1 8. So 8 plus 4 plus 2 plus 1 is 15. No 16s, no 32, no 64s. So that's our 15. So now we need to get minus 7. And minus 7 in 2's complement, because we're now saying, in this case here, we've 7 bits for the magnitude. So we have 1, 2, 3, 4, 1, 1, 1. So that's going to be positive 7 in 7 bits. So now to get minus 7, we have to get the complement of this. So the complement of this is, we get the 1's complement. So the 1's complement, we invert all the bits. 1, 1, 1, 1, 0, 0, 0. And then we add on 1. And to add on 1 onto this gives us 1, 1, 1, 1, 1, 1, 0, 0, 1. So that's the number that we're now adding to our 15. So we've got minus 1, 1, 1, 1, 0, 0, 1. Okay, so now we add them all together. Change the color. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 0 with a carry of 1. 1 plus 1 plus 1 is 1 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0. Carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1, 0 with a carry of 1. Again, we've ended up with this, in this case, 9th bit that we just ignore. So now we've got this that says 0, which is positive. And we've no 64s, no 32s, no 16s. We've 1 8, no 4s, 2s, or 1s. So this is positive 8. And again, the solution is plus 8. And that's correct. But you'll see that the representation of minus 7 is much different this case because we have an awful lot more leading ones, because its complement form has to take account of the full width of the binary value. So this question, the third question, says perform 22 minus 28 using 6-bit 2's complement form. So 22 minus 28 are bigger numbers than we've used before. So the first question we have to ask is, do they actually fit within the range? So we know that for a 6-bit 2's complement form number, we're in the range of 2 to the power or minus 2 to the n minus 1 to the range of plus 2 to the n minus 1 minus 1. So minus 2 to the n minus 1, so n is 6. So that will be 6 minus 1 is 5. So minus 2 to the power of 5 as far as 2 to the n minus 1. So plus 2 to the 5 minus 1. 2 to the 5 is 32. So that will be minus 32 up to 2 to the 5 is 32 minus 1 is 31 or plus 31. So we can see that, well, 22 is less than 31. So it's in the range between those two numbers. And minus 28 is greater than minus 32, so therefore it's in that range as well. So we can represent both of these numbers, 22 and minus 28, validly using a 6-bit 2's complement form. So let's do the calculation. So we want to do 22 minus 28. So we're going to do 22 plus minus 28. That's the calculation we're going to do. So we know the result is going to be minus 6. But let's represent 22 first of all. So we could repeatedly divide by 2. We know it's positive first of all. So we could repeatedly divide 22 by 2 and find out the bits for this. But instead we're just going to do a best fit. So 16 fits into it. And we can say 16. In this case, if we take 16 in, we have a remainder of 6. So 8 doesn't fit. 4 would fit in to 6, obviously, and 2 and 0. So we can say that this is going to be 22 is 16 plus 4, which is 20, plus 2 plus no 1s is 22. We also have to find out, well, what is minus 28 when we want to represent it in 2's complement form. So to do this, we need to start off with 28. So what's 28? Well, 28 is going to be 16 plus 8 is 24, plus 4 is 28. So we have 5 bits to represent the magnitude. So 28, 16, 8, and 4. To get minus 28, we get the complement. So we get the 1's complement, which will be 0, 0, 0, 1, 1. And we want to add 1 to that. So this becomes 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 0, 0. So 0, 0, 1, 0, 0 is the magnitude of minus 28. So we write a 1 to say the sign is negative, and we write in the values. So 0, 0, 1, 0, 0. So that's minus 28. So let's do the addition. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0 with a carry of 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. So straight away you can see that we didn't get this extra bit this time, but what we have is a 1 here, which means that our result is negative. Which means that if we want to actually find out what this magnitude is in decimal, we need to get the 2's complement of this value in order to work out what the magnitude is. So how do we get the 2's complement? Well, we'll write it down. 1, 1, 0, 1, 0. We get the 1's complement by inverting it. So it becomes 0, 0, 1, 0, 1. And we add on 1. So we add 1 to that. 1 plus 1 is 0. Carry 1. 1 plus 0 is 1. 1, 0, 0. So it's 0, 0, 1, 1, which is 1, 4, and 1, 2, which is 6. So this says that the result is negative and the magnitude is 6. So we're saying that 22 minus 28 is minus 6. So that's correct. And we've shown that works correctly. So next we're going to do multiplication with the 2's complement form and show that it works correctly. So in this case here we want to multiply 5 multiplied by 3. So again, both numbers are positive, so it's plus 5 multiplied by plus 3. So we represent 5 and we're using 5-bit 2's complement, so we're using 1 bit for the sign bit, so it's positive, and 4 bits for the magnitude. Now the 4th bit of magnitude will be 8s, so there's no 8s, so 4 plus 1 is 5. For 3, we want to multiply it's positive as well, and to represent 3, it's 2 plus 1 gives us a value of 3. So we want to do this as our multiplication. And the way we multiply is we simply do it like we would with binary, or with decimal rather. We simply multiply the numbers across. So the very first time we say 1 times this number here. So 1 times the number above, 1, 0, 1, 0, 0. Then we shift one position to the left, just like we would if we were multiplying in decimal, and we now multiply this number. 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, and so on, 0, 0. And we continue on, but because the remaining values are all 0, it means they're all going to resolve to 0, so there's no need to go any further there. So we can stop at this point here. And then we simply add the values together. So when we add these together, we're saying nothing plus 1 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0, and then we ignore the rest of the bits. Even if 0, it doesn't matter. We ignore it because, again, we have a 5-bit computer, if you like. So our result is 0, which is positive, and the magnitude is 1, 8 plus 4 plus 2 plus 1, which is positive 15. So this says that 5 multiplied by 3 is equal to 15, and that's correct. So if we take a slightly more complicated example, in this case here, we want to multiply minus 5 by 3. So we want to see that it works for negative numbers as well. So the first question is, what is minus 5 in a 5-bit 2's complement form? Well, even if we include the sign bit for plus 5, well, the sign bit for plus 5, so if we've used the full 5 bits, 0, 0, 4 plus 1, that says that's positive 5 with a 0 on the front. So minus 5 is going to be the 1's complement of this, which is 1, 1, 0, 1, 0, plus 1 to get the 2's complement. We add that on, 1, 1, 0, 1, 1. So that's minus 5 in our 2's complement form. So let's write it down like that. So we want to go minus 5 multiplied by plus 3. I'll just write down as 3. So leave a bit of space because we're multiplying. So that's 1, 1, 0, 1, 1, where this is our sign bit, and these are all our magnitude, times plus 3. So plus 3 is positive, 0, 0, 1, 1. So we want to do this calculation exactly the same as before. So 1 times 1 times this number is 1, 1, 0, 1, 1. We shift over one space and then we do the same thing again. 1, 1, 0, 1, 1. And because the rest of the values are 0, we don't need to fill them in, so we can simply finish at that. Now we add all the bits together. So nothing plus 1 is 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 plus 1 is 1 with a carry of 1. 1 plus 1 is 0 with a carry of 1. Again, we don't have a 6th bit or a 7th bit in this case, so we can simply cut these bits out. So we cut that out, cut that bit out there. What we're left with now is we're left with a 1 here, which says that this is a negative number, and we're left with a value of 0, 0, 0, 1. So if we want to find out what the decimal equivalent of this is, well, we have to go and get the 2's complement of 0, 0, 0, 0, 1. So what's the 2's complement? We invert the bits, 1, 1, 1, 0, plus 1 gives us 1, 1, 1, 1. So that's 15. So we can say this is negative 15. So minus 15. So minus 5 multiplied by 3 is minus 15. And again, this holds true for the 2's complement form. So if we want to check that this is commutative and we want to reverse the operation, instead of minus 5 times 3, we do 3 times minus 5. We still have to go through the same steps. So we need to find out, we're still using 5-bit 2's complement. So again, we need to find out what is the value of minus 5. Well, plus 5 is going to be 0, 0, 1, 0, 1 as before. We get the 1's complement, which is 1, 1, 0, 1, 0. We add on 1 and we get 1, 1, 0, 1, 1. So that's minus 5 in our 2's complement form. So now we're going to say, well, let's multiply 3 as plus 3 multiplied by minus 5. And I'm going to give myself a bit of room here because we'll see we're going to need a bit of room. So I'll try and keep it square with the squares. So 3 is going to be positive 3, so 0. And then we 4 bits for the magnitude, 0, 0, 1, 1. So that's 1 plus 2 is 3. Minus 5, we've just seen, is 1, 1, 0, 1, 1. 1, 1, 0, 1, 1. So just draw my line. Okay, so we're going to multiply it out. So let's multiply it out. So 1 times the number above is going to be 1, 1, well, it's going to be the number above. Now we shift over one position to the left, a left shift, and we do 1 times the number above. Zero, just to be complete. Now we do 0 times, so we shift over again, and we do 0 times. I'm just going to do it for completeness here. 0 times all the bits above, so that'd be 0, 0, 0, 0, 0. Now 1 time the number above, 1, 1, 0, 0, 0, and again 1 time the number above after shifting over to the left again. Okay, draw my line at the bottom. So now what we have to do is you can see why the position was so important. We now need to add up all these digits together. So 1 plus nothing is 1. Let's change my brush. 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 is 0 with a carry of 1. 1 plus 1 plus 1 is 1 with a carry of 1. 1 plus 1 is 0 with a carry of 1. And we go to here. And again, we're left with the same issue again, in that we've only got 5 bits. So 1, 2, 3, 4, 5. We simply remove the last bit. We ignore those bits. So this leaves us with a number. So we've got a 1 here, which means it's negative. And 0, 0, 0, 1 is our magnitude, but it's in complement form. So again, we do the same thing again. 0, 0, 0, 1. We get the complement of that. 1, 1, 1, 0. Plus 1, which is 1, 1, 1, 1, which is 15. So again, we get negative 15. So that shows that this is commutative, that it doesn't matter what the order of the operands are when we do an operation like multiplication, we see that we get the same result. Albeit in this case it's longer, and obviously if you're trying to multiply numbers together, you try and put the 1 with the most zeros, at the leading zeros, on the bottom and not on the top if you're doing it by hand on paper.
So hopefully now you have an understanding of the 2's complement form, why it is needed, and how we can perform arithmetic operations with it. At this point I have shown you that the form works perfectly for standard arithmetic operations, and I've pointed out that you need to define the size of the binary words you are using, as a 2's complement is different if you represent a negative decimal number with 4 bits or with 5 bits. In the next video I'll talk about the problems that can arise if you use numbers that are too big for your architecture, which results in a condition called overflow that gives you inconsistent results. You can follow the link for that video here.